Assalamualaikum to Dr. ARIF. We are from Group 1. Would like to present to you Experiment 8, which is heat transfer coefficient in Dropwise and film condensation. So this is our team members. Our group consists of 4 members, which are Alia Nasuha, me Nur Izzatun Nazla, Nur Farisha Idina, and Putri Nur Emilia Raslina. The first one is introduction. In this experiment, there are 2 forms of condensation, which are dropwise and film. So the steam will condense on either of these 2 surfaces. Condensation will occur when saturated vapor comes into contact with lower temperature surface. When the rate of condensation is low in dropwise condensation, vapor condenses on the surface into smaller droplets of varying sizes. These droplets move downhill, collecting static droplets along the way. The process of film condensation wets the surface and forms a laminar film of vapor that covers the whole surface. This film can then travel downward, thickening as more vapor is taken up along the route. In this film-wise condensation process, heat is transmitted from the vapor to the cooling medium via the condensate film created on the surface, whereas in the dropwise condensation process, just a portion of the surface is coated with condensate. A very high heat transfer rates are recorded in the dropwise method due to strong contact between the vapor and the surface. It is far more efficient and provides a faster rate of heat transfer, but it is difficult to maintain consistently. Thus, industrial equipment is typically operated in a film-wise condensation. In order to increase the efficiency of this condenser, this experiment has been utilized in some of the industries. Vapor power cycles like Rankine cycle are one of the examples for this experiment. The operational pressure of the condenser can be decreased and the total efficiency of the cycle can be reached by enhancing its efficiency. The next one are objective and scope. The objective is to determine the heat transfer coefficient for the dropwise and film condensation using the condensation process demonstration unit. The second one is to observe the difference of droplets on film and dropwise through condensation. The scope that we get is to compare the heat transfer in both film-wise and dropwise condensation, and to compare the outlet temperature in dropwise and film condensation. Lastly is to evaluate the heat coefficient in dropwise and film condensation.
For the theory and working principles, condensation of a vapor to a liquid and vaporization of a liquid to a vapor both involve a change of phase of a fluid with large heat transfer coefficients. The experiment focused on the condensation process as well as on the condensing process with constant pressure. The fluid that is used in this experiment is water. A layer of condensation forms on the cool surface during film-wise condensation, providing barrier to the heat transfer. The flow in this layer, which is normally downwards, can be laminar or somewhat turbulent with a rippled surface. Under some conditions, dropwise condensation will yield a surface heat transfer coefficient that is 5 to 10 times greater than the film-wise condensation. This is the formula related to the heat transfer coefficients. Alpha equal to Q divided by A times in bracket Ts minus Tw, where Q is equal to transfer thermal power with the formula of Q equal to mCp times in the bracket of T out minus T in. Cp referred as the specific heat capacity of water, A is the condenser surface area, while Ts minus Tw is the temperature difference between the saturated vapor and also the wall of condenser.
The next one is experimental setup. So these are the apparatus that we use in this experiment, which is heat transfer coefficient in dropwise and film condensation. We can see on the left side is the flow rate valve that we use in this experiment, and on the right side is the data that we need to record in the table.
For the methodology part, first and foremost, we need to turn on the switch to ensure that the system operates well. Second, open the water source near the experimental setup. Third, turn on the main switch and regulate power knob to 60 watt, followed by heater switch. Third, turn on the main switch. Fourth, adjust the inlet valve to the condenser, which is V1 and V2, by rotating them anti-clockwise and also increase it. For step 5, the cooling water flow rate is circulated to minimum value of 0 liter per hour. For step 6, the system is let to stabilize for 5 to 10 minutes in order for the condensation process to take place, and then the initial reading will be recorded. 7. Tabulate the data recorded for values of inlet, outlet, surface, and steam temperature. 8. Make adjustment if required. Then repeat the experiments from step 4 to 8 by increasing the inlet water flow rate gradually. After the experiment is done, switch off the heater, main switch, and also power.
Okay, we will continue to the calculation part. First, this is the data that we obtained from the experiment. We have to find our mass flow rate, which is the formula is the density of water times by the volumetric flow rate, which is F1. So here, we substitute the density of water, which is 1000 kg per meter cube, times by 0.4, which is our volumetric flow rate in unit liter per hour. We need to cancel out our units, so I multiply it by 1 meter cube over 1000 liter and times by 1 hour over 3600 seconds. So the answer will be 0.00111 kg over second, which is our mass flow rate. For the thermal heat transfer part, which is Q, the formula is Q equals to our mass flow rate times by our Cp of water times by our delta T. Our delta T obtained from this experiment, which is from T2 minus T1. The value of T2, which is 32.5, minus by the value of T1 we obtained from the experiment, which is 28.7 degrees Celsius. So we just substitute in the equation. So the answer for our thermal heat transfer, which is Q, is 23.333 joules per second. Okay, the next part is we have to find our heat transfer coefficient to plot our graph. So the formula as given in the lab manual, which is our thermal heat transfer over area of the condenser times by the difference between temperature of steam minus temperature of water. So we substitute back our delta T here is T7 minus T3. So the answer, and then we substitute into our equation then we substitute to our equation. So our Q is 23.33 in the unit of joule per second, divided by our area of condenser 0.0025 meter squared, and then we times with our delta T. So the answer for our heat transfer coefficient, which is alpha, equals to 162.8010 in the unit of work over meter squared times Celsius. By using these three steps, we can obtain our mass flow rate, thermal heat transfer, and heat transfer coefficient for each volumetric flow rate that we use in our experiment. After we apply all the steps from the previous slide, we will obtain in table 1, which is our volumetric flow rate, inlet temperature, which is T1, outlet temperature, which is T2, our surface temperature T3, and our steam temperature T7. Also, our mass flow rate, thermal heat transfer, and coefficient of heat transfer in film condenser. So this is our graph of coefficient of heat transfer in film condenser against the volumetric flow rate that we obtain when we apply our three steps from the previous slide. Next, this is our table 2, which is contain our volumetric flow rate, inlet temperature T4, outlet temperature T5, and surface temperature T6, and then our steam temperature T7, and our mass flow rate, thermal heat transfer, and coefficient of heat transfer in Dropwise condenser that we calculate before. And we move to our graph. This is a graph of coefficient of heat transfer in Dropwise against our volumetric flow rate.
There are a few discussions that we can discuss for this experiment. The first one, the aim of this experiment is to determine the heat transfer coefficient for the Dropwise and film condensation using the condensation process demonstration unit. Before the experiment is carried out, we decided to use the volumetric flow rate from 0 to 60 liter per hour as data. Second one, gold represents dropwise condensation and copper represents filmwise condensation. Gold has less visible water droplets while copper has very visible water droplets. The third one, from the curves formed in graph 1 and 2, we can see that as the volumetric flow rate increases, the coefficient heat transfer increases as well. And also based on graph 1 and graph 2, dropwise condensation has higher heat transfer coefficient. The film around the copper causing heat resistance more than gold, which will be resulting in the difference of heat transfer coefficient. So we can conclude that condensation is a process where water vapor is turned into liquid water. It can be seen dropwise condensation has a higher heat coefficient than filmwise condensation. Gold has higher heat coefficient due to no film layer to resist the heat. The relationship between the coefficient heat transfer and volumetric flow rate in film and dropwise condensation is dependent to each other. It can be seen from the plotted graph that coefficient heat transfer and volumetric flow rate are directionally proportional to each other both in film and dropwise condensation. There are 3 safety procedures that our group have listed out during the experiment. First, upon shutdown, keep the cooling water flowing for at least 5 minutes through the condensers to cool them down. Second, never operate the heater whenever the water level falls before the heater element, as this may cause a permanent damage to the heater. And the last one, do not touch the glass surface during experiment. There are a few references that we refer to when making this report.